Hello friends, welcome back. Today we are going to see convolution integral for some standard signals. And we are going to see if x of t is convolved with the standard signal called unit impulse signal, what is going to happen. We are going to see when it is convolved with u of t, what is going to happen. And we are also going to see what is the convolution integral of u of t with itself. Okay, so we will start from this first one, convolution with impulse signal. So you know that an impulse signal del of t is an impulse signal which is an impulse present only at t is equal to 0, and otherwise it is the signal is 0 all the time. So we want to see the area of this impulse is 1. Okay, you can't call its amplitude is 1. Okay, so we'll start with this convolution x of t convolved with del of t. We'll write the formula for this. Okay, indirectly we'll use the formula. We'll use x of tau del of t minus tau. So x of tau del of t minus tau d tau. So you know that this tau is varying from minus infinity to infinity. So its tau is varying from minus infinity to infinity. We are writing this both signal in terms of tau. So on the x-axis, instead of t, we are changing the variable to tau and doing the convolution. Okay. So you know this part. Let us look at this part. This multiplication x of tau with del of t minus tau. So del of t minus tau is a signal. Suppose when we are changing it to tau and this impulse is shifted to some instant at t. Okay, so we're going to multiply a signal, random signal x of t. So this is del of t minus tau, and we're going to multiply it with x of tau, the signal. So this will be present only at this instant. Okay, when at t tau is equal to t. So we can call this x of tau multiplied with del of t minus tau. So it is nothing but what I'm writing here is the sampling property of unit impulse signal, that when we are going to multiply this, we are going to get only this instant. So what is this instant? X of t. So this is x of t multiplied with del of t minus tau. Okay, so we're going to put this term in place of this. Okay, so x of t convolved with del of t, you can write this tau varying from minus infinity to infinity. Now we'll change it to x of t del of t minus tau d tau. Okay, now this integration is with respect to tau. So this term x of t does not contain tau. So we can take out this term. So let us take this term out. Del of t minus tau d tau. Okay. Now we will see integration of this impulse starting from minus infinity to infinity. We are going to move this impulse is always having area 1. So if it is shifted, its area is the same. Okay. So we are going to consider this area. Okay, 1. So this integration value will be equal to 1. Okay. So this area is 1 multiplied to x of t. So this answer come out to be x of t. So this is very interesting to see when we convolve a signal, any signal x of t with an impulse signal, we are going to get back the same signal x of t. Okay, it is so interesting to see. Now we'll move to our next convolution integral x of t convolved with u of t. Let us see what is u of t. You know it very well. U of t is the unit step signal. This is u of t. This amplitude is 1 starting from 0 to infinity. Okay. So this is the time index t. So now we need to write this signal x of t convolved with u of t, and Now instead of this del of t, in the formula we'll write u of t minus tau. So how u of t minus tau looks is that question. Okay. So let us draw this. Suppose this is u of t, and if we write in terms of u of tau, it will like this, u of tau in terms of tau. Okay. Now tau is the variable. Now this is the shift. T is the shift, and also this tau is inverse. No, it is minus tau. So I will draw the signal here. This is your u of tau, and this is 1 for 0 to infinity. Okay. Now when you're going to shift this signal, first we'll shift u of tau plus t. U of tau plus t. Let us do this. Tau plus t. So it will shift like this instant t. So t to infinity, this signal will be equal to 1. Okay. Now just we need to flip the signal to get u of t minus tau. So flipping is with respect to this 0 axis. So place the mirror at this point. So this u of, I will write like this for understanding. Okay. So we are flipping this signal. This signal we are flipping. So it will, this minus t point, this will be moved to this point t, and this infinity point will be minus infinity point. Okay. So u of t minus tau signal is starting from minus infinity to t, and its amplitude is still 1. Okay. So when we are going to multiply this signal with x of tau, so x of tau is, let us say, any signal. Okay. Let us write here x of tau. So when we are going to multiply this u of t minus tau with x of tau, what we are going to get? This amplitude is 1. So these amplitudes are preserved. Okay, we are going to get the same amplitudes like this. Again, up to the point t, and after that this is 0. So this signal is also going to be 0. Okay, this is tau, and a signal will be present only up to the point t. Okay, because this u of t minus tau signal is starting from minus infinity to t. So when we look at this formula, let us write it here. Okay. So these limits are going to change because of u of t minus tau. It is starting from minus infinity to t. Okay. So this limits minus infinity to infinity will be changing to minus infinity to up to this point t only. Okay. So only the signal remaining will be x of t, u of t amplitudes will be 1. So we will not write that. Okay. So this convolution x of t convolved with u of t, we can write it as minus infinity up to point t x of tau d tau. So this is our final answer. So we are going to sum all the samples, means integrate all the samples of x of t up to the point t. Okay. So this is just an integral. So we're going to accumulate all the points up to the point t. So it's an integrator. For a signal x of t, it's like an integrator. Okay. So this answer is going to be integration of all the amplitudes of x of t up to the point t data. Okay. Now third one is also simple, u of t convolved with u of t itself. Okay. So u of t we have here. I'll put only u of t minus tau signal here. So let us draw this u of t minus tau. So it is up to the point t, starting from minus infinity. This is, right, this u of t minus tau. Okay, we don't need this now. and we're solving this u of t convolved with u of t. So here I'll make change u of t convolved with u of t. So this signal is also u of t. U of tau convolved with u of tau. So u of tau into u of t minus tau. So we have both the signals, u of tau, u of t minus tau. So u of t is starting from 0 to infinity, and u of t minus tau is starting from minus infinity to instant t. So always when we have u of t in this, so u of t is going to be 0 for this instant, this interval minus infinity to 0. So obviously every time whatever the shift is, every time up to 0 the answer is going to be 0. Okay, and only its amplitude is 1 for the interval 0 to t, and after that, because of this signal is 0, this is going to be 0. So the answer is going to be present only for the interval 0 to t. Okay, so u of t multiplied with u of t minus tau is only present for 0 to t, so we don't need this range now. So we will change this u of t convolved with u of t is equal to integration starting from 0 to t, tau starting from 0 to t. This amplitude is 1 and this is also 1, so 1 multiplied by 1 d tau. Now we'll integrate with respect to tau. So this is going to be tau and limits are 0 to t. So it is going to be t minus 0, it is going to be t. So this t is present for, always it is valid for great t greater than 0, greater than equal to 0. Okay, so we can write like this, and it is equal to d0 for t less than equal to 0. Because we know that u of t, this shift can change, this can go like this and up to this point, but still we are going to get 0 on this side. So this signal is always going to be a causal signal. Okay, so this is t for t greater than equal to 0. So let us, for fun, we'll draw this signal t for t greater than 0. Okay, so for less than 0 values of t, it is going to be 0, and at 0 we'll have amplitude equal to 0. At 0.5 we'll get amplitude equal to 0.5. At 1 we'll get the amplitude is equal to 1. At 2 we'll get the amplitude is equal to 2, like this. So this is going to be a ramp signal. You know ramp signal, it is r of t, and also we'll call it t into u of t. Okay, t into u of t, because that ramp signal is also present only for t greater than 0. Okay, that's why it is called as tu of t. So it is a ramp signal when we multiply, convolve u of t with itself u of t. So u of t convolved with u of t is going to be r of t. So this is very interesting to see these results, and these results, we can use these results directly as a formula in the examples we need to do this kind of convolution integral. We can directly write this x of t convolved with del of t, we can write x of t directly. Okay, when you come across this situation, x of t convolved with u of t, you can write it as an integrator of x of t. Okay, u of t convolved with u of t is r of t. So these results can be directly used, and these are very important results which can be directly used in the numericals of convolution integral. Thank you.